Today we're going to take a look at higher order derivatives, and all that really is saying is that you're going to take the derivative once, and if they're asking for a second order, then you take the derivative of the first derivative. If they're asking you for a third derivative, you take the first derivative, then you take the second derivative of the first, and then you take the derivative again of that second one. It's circular reasoning, I know. And so let's take a look at this. So for the first question, we have the function x to the fifth minus 9x. As you know, the first derivative is 5x to the fourth minus 9. You bring the 5 down, take 1 away from the exponent, and then you get just negative 9 from the second term. That's the first derivative. The second derivative is the derivative of this guy. So we bring the 4 down, multiply it by the 5 to get 20, take 1 away from the exponent to get 3, and the derivative of a constant is 0. So your second derivative is just 20x cubed. For the next one, they're asking us to take the third derivative, so we have to do the derivative 3 times. Let's go ahead and rewrite our function first. X to the fourth remains the same, but 3 over x becomes 3x to the negative 1. It's going to make taking that derivative easier just using the power rule. So the derivative of the first term is 4x cubed, as we see here. Bring the negative down of the second term to get negative 3. X to the, subtract 1 from the exponent, negative 2. So we get 4x cubed minus 3x to the negative 2. Second derivative, take the derivative of that guy. To do that, 3 comes down, multiplies by the 4 to get 12. Take 1 away from the exponent to get the square. Then for the next one, bring the negative 2 down, multiply it to get positive 6, and then x to the negative 3. Take the next derivative of the second one to get the third derivative. 2 times 12 is 24. Subtract 1 from the exponent to get 1, which we just assume is there. We do not need to write it. And then bring the negative 3 down to be negative 18. Subtract 1 from the exponent to get negative 4, so you get negative 18x to the negative 4. For the third example, the function called a, we have our function written as x raised to the 3 halves minus 5x. This notation of d2a over dx squared is really just another functional notation. Remember, for derivatives that we have, that's what it looks like when you're trying to do higher order, not just first derivatives. So the first derivative of a with respect to x has this notation and this notation. So we bring the 3 halves down in front, subtract 1 from 3 halves to get 1 half. Derivative of negative 5x is negative 5. We need the second derivative, so let's do it again. Bring the 1 half down, you get 3 over 4. Take 1 away from that exponent to get negative 1 half. Derivative of a constant is just 0, and so you'll have a 0 here, so that is the second derivative. I would like you to pause the video, go ahead and do the next 6 derivatives. They're product and quotient rules that you've done before, and then come on back on and take a look at the key. So here is the key for those first 6. Pause the video so you can check your work. And let's go then to word problems. Oops, sorry. Here we go to word problems. And for this one, we're asked to find to find equations of tangent lines. For this one, for number 1, finding that tangent line at a given x, we've done that before, so I think you can do that one and come back and check it. For number 8, sorry, extra words in here. For number 8, I would like you to go ahead and try that on your own. What's different is they want it horizontal, so you just set the derivative equal to 0. For number 9, they're telling you a different number instead of 0. They're telling you it's slope of 9, so you set it equal to 9. So all 3 of these are very similar processes, but a little different in the initial setup that you do. So go ahead and do those, then come back and check the key. Skip number 10, please. And then looking at number 11, these are second derivatives. I think after you've done the front page, you can do this one as well. Just be careful, because when you do the product rule. Here for this guy, you do the power rule and get a chain rule out, so you end up with this. Then you have to use the product rule on that. So here are first derivatives that look a little different than the original functions. For the second one, I went ahead and wrote that denominator with a negative exponent to use the product rule on it. You can use the quotient rule on this if you want to. The second derivative becomes a little ugly, but still possible. On the next one, you can actually simplify that before you run the derivatives. And look, you get a nice pretty little derivative at the end. So go through the details and then check your work on those. For the last page, the new idea we haven't covered in class yet is that when you have a function that gives you position of some kind of activity in motion, so here we have the position of a car, saying that we are going to drive it when it starts moving. So you get position, and then when you take the derivative of that position, you get velocity. And when you take the derivative of the velocity, you get acceleration. And it's because as position changes, that's velocity. As velocity increases or decreases, that's acceleration, deceleration. So that's why the velocity is the first derivative of the position function, and then the derivative of the velocity function is acceleration. Or you can look at this acceleration as being the second derivative of the position function. So now that you know that, I would like you to pause the video and go ahead and answer those questions down below, and then come back and check your work afterwards. So there are the first ones, and then the ones at the bottom. So that's it. I hope you're having a great day.